All right, so matrix operations, the thing we're going to talk about is the determinant. Determinant of a matrix. All right. When you're dealing with a determinant, it's like a property of a matrix. It's a number that we can build for that. And if that number is non-zero or anything other than zero, then that means that that's an invertible matrix. And it's, well, the actual linear algebra term is non-singular, or a singular matrix and non-singular matrix. It's based on what the determinant of that matrix is. A matrix, to be able to find the determinant of that, it must be a square matrix. Square matrices only. What's it mean to be square? Matrix in same rows and columns, so like 3 by 3, 2 by 2, 14 by 14, n by n. Gotta have the same number of rows and columns to be able to find the determinant of that. And can be done by hand. We'll do 2 by 2s by hand, but anything bigger than that gets into quite a few operations in order to get the determinant of anything bigger than a 2 by 2. 2 by 2s, 3 operations. It's pretty quick and easy. But anything bigger than that, depending on the numbers that are in the determinant, how many, if there are any shortcuts to that. So we'll talk about 2 by 2s first. So on a 2 by 2 matrix, maybe it's A, B, C, and D as the elements of that matrix. To find the determinant, the notation that they might use would be the most obvious one is when they say DET of A, B, C, D. They'll actually write DET out beside it. That just means find the determinant. The other notation that they might use is big absolute value marks. That's what they look like, but it has the matrix in it. That is also notation for find the determinant of that. You may not have any instructions there. You just know if it's big absolute value marks, it's determinant out of that. And the way that you're going to find determinant of a 2 by 2, you can do it with a calculator. We'll do it with a calculator as well, but I want to show you how quick it is to do without it. You just cross multiply A times D minus D times C. That gets you a number. That number is the determinant of that matrix. Okay, so 2 by 2s, you got 2 multiplications and 1 subtraction. That's 3 operations. I rarely do 2 by 2s with the calculator. It can be done though, and I'll show you that. Most everything bigger than that, I'm absolutely fine with you doing it by calculator method. But 2 by 2s, you're probably just going to be thinking it's quicker to just do it by hand. So let's do the determinant of 2, -1, 3, 5. We'll put some numbers in there. So big absolute value mark. So that tells me, hey, you're finding the determinant of this. You're not doing anything else. So that'd be 2 times 5, and I'm writing out that extra step, minus -1 times 3. This will be 10 plus 3, which is 13 out of that. So that's doing it by hand. Took less than 10 seconds. Okay. Calculator-wise, you've got to go through the trouble of typing in that 2 by 2 matrix. So you got to go second matrix, go over to edit, put in a 2 by 2, and then put in the numbers 2, -1, 3, and 5. Second, quit to go back to the regular calculator screen, then second matrix, go over to math, and the very first option is determinant, which is the one you want, and then you got to go tell it which one to do that to. So matrix A is where I put mine, and all of that typing and stuff to get the same answer we got in less than 10 seconds. So 2 by 2s, I generally do by hand. I'm not requiring you to show me doing one by hand, but just understand it's quicker usually to do that. Now, get to a larger matrix, maybe a 3 by 3, 2, -1, 3, -2, 5, 1, 0, 6, 8, 9. Now, there are methods for doing this by hand. If you want to know any of those, feel free to ask me on a work day, and I will gladly show them to you. But I do not require you to know them for college algebra. If you're going into engineering and you're going to have to take a linear algebra class, most likely at most every college you go to, they're going to show you some shortcuts and tricks for doing larger matrices by hand, most likely. I know in my linear algebra class in college, we did a lot of them by hand. Well, all of them by hand. We didn't use a calculator, period. And reason being is we ended up doing a bunch that had like variables in them. And you ended up with equations to solve. Is what it was. But anyway, 3x3 matrix. I'm all for doing that with the calculator. So just punch that matrix into your calculator. 2, -1, 3, -2, 5, 1, 0, 6, -9, and tell it to find the determinant. So second matrix, edit, trace by trace. Thank you very much, Ms. Susan. All right, 2, -1, 3, -2, 5, 1, 0, 6, -9. And then I put that in A. I've already used that command, so I'm just going to copy and paste. And -120 is this number determines if the matrix is invertible or not. We'll get to inverse matrices later on. And the idea is that these square matrices could be the coefficient matrix to a system, and if you know the determinant of the coefficient matrix, if it's anything other than 0, then you know that I can solve that system out of that. So a lot of times it's a quicker calculation. When you get to larger systems of equations, I'm trying to find a rough example of application of this. When you're launching a satellite into space, Falcon Heavy, well, I can't remember what number we're on now, but it launched this week, and Mr. Kimsler's brother was at it. He filmed it and posted on Facebook. Pretty awesome. He goes to a lot of those now. He's retired state trooper, so he has a lot of time on his hands. So he drove down and watched it. But there's a lot of variables involved, right? You got wind speed, you got all these other things. So there's a big system of equations to get the right launch point and the right angle and all that. There's a lot of things that go into that. So a big system of equations goes there. Well, if you've got this system and you're asking obviously a computer program to solve it for you, most likely you're not going to have somebody doing it by hand these days. It takes a ton of resources from that machine, right, to solve a very complex system. Well, you wouldn't want to waste all that time and resource to have it try to solve it if it wasn't even solvable, right? So it would be quicker to determine if it's even got a solution by finding that determinant. Much fewer calculations, much less time involved because you get a number back quick and you know, hey, there is an answer to this, then proceed from there. So a lot of times that's not getting the complete answer, but knowing if there even is one is a good start. And finding that determinant. It's kind of like a property of a matrix. It's not really, doesn't do much as far as doing anything with the matrix. We'll talk about another method for solving systems using determinants in just a second. But it's a property of that matrix, and as long as it's anything other than 0, that means that matrix is invertible. Which means we can solve a system that if it were the coefficient matrix from that. So that's kind of where all this leads back to. All right. So anything bigger than that, as long as it's square, you can tell your calculator to find the determinant of that. If it is, it's going to crank you back a number back as long as it's a square matrix and you tell it to find the determinant. It's going to do that. If you mistype a number, it will give you a different number, no doubt. Okay. There are some interesting things that happen that you would learn in a college or in a college linear algebra class, that if you swap rows, it changes the sign of the determinant. If you swap columns, it changes the sign of the determinant again, and you can do those sort of things and manipulate what you want the determinant to come back as. But that's all, you know. Some of you guys, I think, will go into engineering. I hope, anyway. That's as a math teacher in high school, I kind of hope that we have some engineers come out of our classes. So, you do what? That's a good field. I have a friend who retired from there, made about $80,000 a year, and she retired when she was 48.
Wow.
Yeah. Yeah, exactly. And she had 0 college.
Good deal.
She worked there from the time she was 16. So.
That's awesome.
That's subject to be. All right, so there's this thing called Kramer's rule. And Kramer's rule is a way of using determinants to solve a system of equations. And, you know, we'll take a small system like 2x minus y equals 7, and then 3x plus 5y equals 9. And we'll just show how Kramer's rule works. Okay, so you've got what's called a coefficient matrix. The coefficient matrix are the coefficients of the variables, right? We talked about that the other day. 2, -1, 3, 5. 2, -1, 3, 5. All right, and then you have, we'll call it the X matrix. And the X matrix is where you replace the X values with the solutions, what the equations are equal to. So you would say 7, -1, 3, not 3, 9, and 5. And then you've got the Y matrix, where you replace the coefficients of Y with what the equations are equal to. Seems all random, doesn't it? And it kind of is. It's not. All right, so what you would do is to do the Kramer's rule and to solve this system is to get X. You take the X matrix, take its determinant, divided by the coefficient determinant. You get Y, you take the determinant of the Y matrix, 2, 3, 7, 9, divided by the determinant of the coefficient matrix. Those are going to give you numbers for X and Y, just like solving that system the way we already know how by our REF will. Okay, now here's all of that stuff right there to tell you I don't care if you do Kramer's rule ever. It exists. No, it exists. So if you go into a college algebra or a calculus class or a linear algebra class and they say something about this guy named Kramer and his method for solving systems of equations, oh, Mr. Isbell said something about that. You may have never done it before. That doesn't matter because we already know a pretty good method for solving systems of equations. We already know how to do that. When you're solving a system on a quiz or a test, how am I going to know which one you do? Doesn't matter. Okay, get the same answers no matter which way you do that. Okay, so no Kramer's rule exists. That's general knowledge for a math person, is that there's this thing called Kramer's rule. It's determinants of a matrix to solve a system of equations. That's all you really need to know about Kramer's rule. I don't care if you ever do it for college algebra purposes. It won't come back up again in pre-cal. If you're planning on taking that, don't worry. Coach Mack and I have discussed this many times, and we know that Kramer's rule is neat. Well, no, it's not useless. So let's move on. Matrix operations. Matrix operations. First one we'll talk about is the easiest one. Scalar multiplication. think distribute. Distribute, as some folks would say, but it's distribute. It would be like you have a number out in the front of a matrix of any size. There are no size restrictions for scalar multiplication. It works on every size matrix ever. Okay, so all it means is you take 2 and you multiply it times everything on, or -2 in this case, times everything that's on the inside. It's like distributive property. So we end up with -6, -12, -8, -16, +12, -14, 10, -6, 0. So this is the matrix after we've done scalar multiplication. Remember, there are no rules for sizes on scalar multiplication. You can multiply by a scalar no matter what. That scalar can be any kind of number. It can be, here we have an integer. It could be a fraction. It could be a irrational number like square root of 2 or something like that. So no restrictions really on scalar multiplication. It's just multiplying. So, anything that's a real number, you're good with. Okay? So easy stuff. Did that in Algebra 2, so it should be easy. So if we add and subtract matrices, what do we know from Algebra 2? They got to be the same size. Good deal. That means exactly the same size. So if I'm going to take a matrix here, 2, -6, -5, 8, 10, -11. What size is that matrix? 3 by 2. So to add something to that or subtract, it's got to be the exact same size. 3 by 2. So -5, -8, 13, 6, -14, 4. So again, this is a 3 by 2 plus a 3 by 2. Got to be the exact same size, or it's not a defined operation. So if it's not the same size, then you just say it's undefined operation. Can't do that. Okay, so here they are the same size. You just add matching elements. I generally don't do matrix addition with calculator. You can if you want to. You just put matrix A in as this, matrix B in as that, and then tell your calculator matrix A plus matrix B, and it will give you the answer. I'm not going to go through typing that in the calculator. You guys are smart enough to do that. So that'd be -3, -14, 8, 14, -4, and -7. And that would be the sum matrix for those two. But again, it's got to be the exact same size for addition and subtraction. They can mix in scalar multiplication into addition and subtraction. Order of operations still applies. Multiplication happens before addition and subtraction. So if there's a scalar multiplier on one of the matrices, multiply it out before you add. Okay, so just like you would with regular numbers. You want to do it in order of operations style. All right. Next operation is multiplying matrices. Row by column, row by column. These must match. Not that you have to have the exact same size. A lot of times the exact same size matrices won't multiply together because the columns in the left matrix don't match the rows in the right matrix. And it does matter what order they're written in. Multiplication with matrices is not commutative. Okay? Not commutative. Means you can't swap the order. So if it's written matrix A is on the left and matrix B is on the right, A times B does not necessarily match B times A like it does with regular numbers. 3 times 2 is 6, just like 2 times 3 is 6 in regular numbers. But with matrices, it doesn't always work. It doesn't work that way very often, only with certain types of matrices. Does that work? So here's what happens if you've got a 2 by 3 times a 3 by 4. The middle numbers match. So that's just the dimensions of the matrix. If the middle parts match, then when you multiply that out, you're going to get a 2 by 4 as the answer. The matrix that you're going to get for an answer is going to be size 2 by 4. So be able to determine what size a matrix will be when you multiply two together. If these do not match in the middle, then it's an undefined operation. Just like if your addition and subtraction are not the exact same size. It's an undefined operation. Okay. Multiplying matrices by hand is not hard, but
Hunter Hudson, Chance English, reports to office.
all right. 5, -7, -8, 12. Let's say 2. Let's do a easy one. So this is a 3 by 2, and this is a 2 by 1. Is that a defined operation? Yes. These match. So that means we're going to get what size matrix as an answer? 3 by 1. All right. Now, if you want to do this by hand, I like doing these by hand. It's fun. Math is fun. You take the row times the column, and you match up pieces. 2 times 10 plus -3 times 11. And that's the first piece. And then 5 times 10, -7 times 11. Add those together, and that's the second part of that column. And then -8 times 10 plus 12 times 11, and that's the third part of that column. But I don't expect you to do matrix multiplication by hand. I am absolutely fine with you doing this calculator. So I would go second matrix, go over to edit, use matrix A, and put in that 3 by 2, and get 2, -3, 5, -7, -8, 12. All right. And then I'd go back to the matrix menu, go to edit, and in matrix B, I've got a 2 by 1, size 10, or number 10 and number 11 in it. Wonderful, fun stuff. And then I'm going to tell my calculator to go second matrix, pick up matrix A times matrix B. And there I have -13, -27, 52, a 3 by 1, 3 rows, 1 column. Again, I don't expect you to do matrix multiplication by hand. If you want to learn how to do that a little bit better, I'll be glad to show you on the work day if you want to do that, but I don't require you to be able to do that by hand. All right. All right, next thing is inverse matrices. To find an inverse matrix, it must be a square matrix with determinant that does not equal 0. Okay. To find the inverse of a matrix. Finding the inverse of a matrix, we're going to do it with a calculator, but you can do it by hand, and it takes those row operations that we talked about in the first 2 sections, and you've got to come up with your own row operations. I'm not going to tell you which ones to do, and you've got to do what you end up doing is, let's just take an example. Let's take matrix A, and it's 3, -5, 6, 4. Just a 2 by 2 there to start off with. What you end up doing to find it by hand, you take that 3, -5, 6, 4, and put the identity matrix beside it. And what you do is row operations until it flips, and the 1, 0, 0, 1's on the left side, and whatever numbers are on the right side now is the inverse. That's it depending on what numbers are there and what row operations you choose, it can be faster. It can be take a few steps along the way. Again, I'm not requiring you to do that. I don't want you to have to go through that. If you take linear algebra in college, you'll figure that out. If you want to know how to do that, again, see me on work day. I'll be glad to show you. And then you'll go back and do it with your calculator probably. So, because it's tedious and not that the math is hard. It's tedious. So let's go to our matrix and let's enter in that 2 by 2. And again, it's any square matrix. We put that in there 2 or 3, -5, 6, 4. Get out of the matrix menu, go back to the regular calculator screen, and we're going to pick up the matrix we're going to find the inverse for. So second matrix, under the names, I put it in matrix A, and then your calculator has an inverse button. It's right there. It's the x to the -1 power. So just hit that button to get the little -1 exponent to show up there, and then hit enter, and it'll invert that matrix. Now it gives a mindset to give me decimals out of that, so I want to change that to fractions. So I hit math, enter, and it cranks it back into fraction form there. So 2 over 21, 5 over 42. -1 over 7, 1 over 14. Is that right? Yeah. And there's the inverse of that matrix. If it is a non-singular matrix, which means the determinant is 0, and you tried to do that with a calculator, it give you an error. And you can't do that. So it's kind of foolproof for this stuff. It's not, we're not doing anything fancy on that. Now, here's what, how can you verify that two matrices are inverses of one another? Well, one way would be put the matrix in there and then find the inverse of it. See if it matches the other one. The other way to verify that is by matrix multiplication. So I'll show you that because I think it's good to know this little bit of information. And I still got like 10 minutes in class, so I got to fill it up, right? All right, so inverses. Think about numbers. What's the multiplicative inverse of 3? No, that's the additive inverse. What's the multiplicative inverse? Wow. What's another name for it? Reciprocal is another name for multiplicative inverse. What's 3 times 1/3? 1. Okay. 1 is what's called the multiplicative identity, because it's called an identity because no matter what I multiply times 1, I get back that same thing. That's what makes an identity. The additive identity in math is 0 because 7 plus 0 gives me back 7. So an identity gives you, it's like a mirror. It gives you back exactly what you started with. All right. So with inverses on matrices, if I multiply matrix A times its inverse, I'm going to get back the identity matrix. So for our example, from example F, we'll call this example, we know matrix A was 3, -5, 6, 4. We'll call that matrix A. And I don't know, I'm going to use the inverse here, but let's say they gave me those two and said, verify that they are inverses of one another using multiplication. What you would do is you would multiply A times B. And because we already know that those are inverses of other, because we found that matrix B, when I do that multiplication, then I would get back the identity matrix of the same size. And the identity matrix has a diagonal of 1 starting in the top left and going down to the bottom right. Okay, so this is a 2 by 2 identity. That's actually called I2 is the notation for that. I3 looks like this. It's got 1, 0, 0, 0, 1, 0, 0, 0, 1. Where have we seen that? When we were doing the systems of equations, we do that RREF. The identity matrix is on the left side, and the answers are on the right in that last column. So an I4, obviously just continues that trend. But each one of those is going to come from the size of your matrix. Remember, we can't find. We're only able to invert square matrices, so it's going to be a square matrix. When you multiply it back, two matrices multiplied together, if they get you an identity matrix, they're inverses of one another. If they get anything else, they're not. Okay? So that works out wonderfully to verify that two matrices are inverses of one another. All right, practice problems. 878, 7 through 42, 893, 9 through 40, skip a few, and go to 67 through 70. We leave out some of that second section. Monday will be a work day, and a quiz on Tuesday. Keep in mind, college algebra, our final is the 2nd of May, so we're getting close to the end. So that means chapter 12 will end soon.